Okay, math nerds, let's learn about bounded sets. Now, if capital A is a subset of the real numbers and alpha is an element of the real numbers, so alpha is just one particular number, but there's the following property. For any element of the set A, x is less than or equal to alpha. Then alpha is called an upper bound of A. Alpha is bigger than or equal to every single element of the set A. On the other hand, if you have the opposite inequality, where alpha is less than or equal to every element of the set, then we call alpha a lower bound of A. If A is a subset of the real numbers and there is some number which is an upper bound, then we say the set is bounded above. So if it has an upper bound, it is bounded above, and vice versa. If, however, there is a real number which is a lower bound, we say it's bounded below. If a set is bounded above and bounded below, then we say it is bounded. If it's not bounded, we say it's unbounded, and we can say unbounded above or unbounded below, or we could just say unbounded. So some little examples of some sets that might be bounded. So we could, for example, we could have, here's the number line. The set A could be everything from -6 to 2, then the single element 10. Okay. Now, if I let alpha be, say, 28, way up here, everything in this interval and the number 10 are all less than or equal to alpha, so alpha is an upper bound. It's certainly not the only upper bound. 27, 26, 4,011,000,011, all upper bounds as well. Now this particular set is bounded above because it has an upper bound, but it also has a lower bound, like -10. Everything in the set is bigger than or equal to -10, so this set is also bounded below, and if it's bounded above and bounded below, then you can call it bounded. Okay, so a quick result. Suppose A is bounded above and B is a subset of A. Then B is also bounded above. So we assume that A is bounded above. What's the definition of that? There is a real number, we'll call it alpha, so that alpha is an upper bound of A. Now we claim that this number alpha is also an upper bound of B. So if I take any element of B, I need to show that it's less than or equal to alpha. But B was a subset of A, so if x is in B, x is also in A. And what did I know about alpha? It was an upper bound on A. Therefore, x is less than or equal to alpha. And this was for an arbitrary element of B. So since x is less than or equal to alpha for any element of B, we say alpha is an upper bound of B. By definition, therefore the set B is bounded above. Isn't this obvious? Yeah, well, kinda. Okay, if I have a set that has an upper bound, and then I only take some elements of that set, it's still bounded above. Okay, so if I have the real number line, and I have a set A, which is bounded above by alpha, and now I'm going to form a set B by taking a subset, maybe this little interval, this point, this interval, this point, and then a little interval here. Since it has to be contained within A, it was a subset of A, it has the same upper bounds, possibly more upper bounds. Okay, it's possible for B to have upper bounds that A didn't. So maybe if this is all A, and then for B, I just take this bit right here. Now this number here will be an upper bound of B. Everything in B is less than or equal to this alpha, but not everything in A was less than or equal to this alpha. So a subset can have different upper bounds than the original, but it definitely has some upper bounds if the original did as well. So pause the video now and try to work through these sample problems. There's a bunch of them, but a lot of them are pretty quick and they're all pretty important. Pause the video, work through the problems. So hopefully you had some luck. You were able to prove some, if not all of these. Now let's talk about arithmetic on sets and how it interacts with bounds. So suppose A and B are both bounded above. So A is a set that has an upper bound and B is a set that has an upper bound. I claim the set A plus B is also bounded above. Now, since A has an upper bound, I'm going to call it alpha, and B has an upper bound, I'm going to call it beta. I can call them whatever I want, doesn't really matter, but A with alpha, B with beta makes sense. Now the claim is that alpha plus beta is in fact an upper bound on the set A plus B. So, to prove that this set A plus B has the upper bound alpha plus beta, I need to take an arbitrary element of A plus B, and the goal is now to show is x less than or equal to alpha plus beta. But since x is from the set A plus B, it must be of the form something from A plus something from B. I'll call the first one y1 and the second one y2. Something from A, something from B. But since y1 is an element of A and alpha is an upper bound on A, then y1 is less than or equal to alpha. Since y2 is an element of B and beta is an upper bound of B, y2 must be less than or equal to beta. And if y1 is less than or equal to alpha and y2 is less than or equal to beta, their sum is less than or equal to alpha plus beta. So any element of the sum set A plus B is less than or equal to alpha plus beta. By definition, alpha plus beta is an upper bound of the set A plus B. Okay, here are a couple of similar problems. Again, some of them are straightforward, some of them aren't, but they're all going to be fairly important. So go ahead and pause and work through them now. Take a minute to comment, subscribe, get notifications, whatever other things you do on the intertubes these days. So hopefully we paused, worked through these problems. That's great. Moving on. We're going to close with a new topic and some new definitions. So suppose I have a set A, it is bounded above and it's not empty. On the previous slide, you would have established a couple things about such a set. If it's bounded above, it has an upper bound, but then every number larger than that is also an upper bound. Therefore, the set of upper bounds is not bounded above. But if the set is non-empty, the set of upper bounds is bounded below. Also, the set of upper bounds must be an interval. So if I have a set A, which is bounded above and not empty, then I ask, what are all possible upper bounds? It's got to be an interval, which is unbounded above but not unbounded below. The only two possibilities are, it includes a left endpoint or it doesn't, but then it has to go off to infinity. So which one are we actually going to have? So let's take a look at some drawings of possible sets. So if I have a set A, here's our number line. Here's my set A. If this is an upper bound, then all of these are also upper bounds. It goes off to infinity. The question is, as I move left, is there going to be a point where this is an upper bound, but I can't move left and still be an upper bound? Is this point going to be an upper bound or not? Okay, is the set of possible upper bounds, so here's my set A, is the set of all possible upper bounds, which I will draw in blue, it's going to include all of this. Is it going to include this, or is it not going to include it? Is the set of upper bounds going to have a left endpoint or not? So in the first case, there would be an alpha, which is an upper bound. Okay, I'm including it in the set of upper bounds, but anything less than it is not an upper bound. In other words, there is a number which is the smallest upper bound, and it is an upper bound. In the second example, there is no such thing as the smallest upper bound, because alpha itself is not an upper bound. But anything bigger than alpha is. Okay, so there would be no smallest number bigger than alpha. So there's no such thing as the smallest upper bound in that case. So which one are we going to have? Are we guaranteed to have a smallest upper bound that is an upper bound? Is there no such thing as a smallest upper bound, or are both possibilities? So Gary guesses that the smallest bound is a bound. Delaney thinks it's the opposite. Ethel hopes we're going to clear it up. Lambo just is kind of indifferent. Okay, so which one are we going to get? Now, if alpha is an upper bound that has the property that nothing smaller than it is, this is that first scenario where the set of upper bounds has an endpoint and includes it. We call that the supremum of the set. If the set of lower bounds actually has a right endpoint that is a lower bound, we call that the infimum of a set. Okay. As a matter of convention, if a set is unbounded above, it has no upper bounds, but we call its supremum to be infinity, and if it's unbounded below, we say its infimum is minus infinity. This is just a matter of form, it's just a declaration. So, if A and B are real, are subsets of the reals, which have supremums, we have left aside whether these things ever actually exist, or sometimes exist, or never exist. Suppose they do. Alpha is the supremum of A. It's an upper bound of A, and everything smaller than it is not. And beta is an upper bound of B, and everything smaller than it isn't. The claim is that if both of those two things are true, then A plus B has a supremum, and it is alpha plus beta. So we want to show that alpha plus beta is an upper bound and of A plus B, and nothing smaller than alpha plus beta is an upper bound of B. So we got to do that in two separate steps. First, we're going to show alpha plus beta is an upper bound. So alpha is an upper bound of A because it's the supremum, and beta is an upper bound of B because it's the supremum. The supremum of a set is an upper bound of the set. So we earlier showed if alpha is an upper bound of A and beta is an upper bound of B, then alpha plus beta is an upper bound of A plus B. So the supremum of A plus B, if it exists, has to be an upper bound. Alpha plus beta is an upper bound of A plus B. What we now need to show is that nothing smaller than it is an upper bound of A plus B. So suppose you pick a number y, which is less than A plus B. We need to show y is not an upper bound of A plus B. Okay, so here's kind of what we are showing. That if I took the set A, which has supremum alpha, and then I took the set B, and it has supremum beta, that then what I do is I'm going to look at the set of all possible sums. We want to show that it has an upper bound of the form alpha plus beta. We have done that. Alpha plus beta is an upper bound of A plus B. So alpha plus beta is an upper bound of A plus B. Now what we've done is we're going to take the real number y, which is less than alpha plus beta, and we want to show that y is not an upper bound of A plus B. In other words, alpha plus beta is an upper bound, but nothing smaller than it is. That is the definition of being the supremum. We assumed that A and B had supremums. Now we want to prove that A plus B does as well, and it's actually exactly alpha plus beta. So we assumed that y is less than alpha plus beta, which means that I can define epsilon to be alpha plus beta minus y. This is a positive number because y is less than alpha plus beta. So epsilon over 2 is also positive. If I take a positive number and I divide it by 2, it's still positive. So if I subtract positive quantities from alpha and beta, I make them smaller. Alpha minus epsilon over 2 is less than alpha, and beta minus epsilon over 2 is less than beta. Why are these epsilon over 2's coming in? We'll see shortly. Now remember what alpha and beta are. They're the supremum of A and B respectively. So not only are they upper bounds, anything less than them is not. So if alpha minus epsilon over 2 is less than alpha, it's not an upper bound of A. Okay, so since alpha minus epsilon over 2 is less than the supremum of A, and beta minus epsilon over 2 is less than the supremum of B, they are not upper bounds on the set. What does it mean to not be an upper bound on the set? Something in the set is bigger than you. So I can find something in A and something in B bigger than alpha minus epsilon over 2 and bigger than beta minus epsilon over 2 respectively. But then I can add them together. If alpha is bigger than alpha minus epsilon over 2 and beta is bigger than beta minus epsilon over 2, when I add them together, I am bigger than alpha plus beta minus epsilon, which was exactly y. So what do we have? There is something in the set A plus B which is bigger than y, and therefore y is not an upper bound on the set A plus B. So not only was alpha plus beta an upper bound of A plus B, nothing bigger than it was, nothing smaller than it was, apologies. So alpha plus beta is an upper bound of A plus B, nothing smaller than it is. That's the definition of being a supremum. Okay, work through the following sample problems here. Again, you're going to be assuming certain things have supremums or infimums. In numbers 2 and 3, you actually need to show a certain number as a supremum, but the set is a very particular form. It's an interval. All right, moving on. Well, not moving on. That's the end. So hopefully that was productive, useful. You learned some stuff. Come on back next time. We're going to keep talking about sets and their structure.